The MT3DMS model is used to simulate the movement of contaminants in groundwater. In this video, we will demonstrate how this model can also be used in GMS to simulate heat transport. We start by comparing the solute transport equation that is solved by MT3DMS with the heat transport equation. Notice that the two equations have the same general form. This term in the heat transport equation is equivalent to the distribution coefficient in the solute transport equation. This term is equivalent to the bulk density in the solute transport equation. Both the distribution coefficient and the bulk density can be specified in the chemical reaction package in the MT3DMS model. Similarly, this term is equivalent to the molecular diffusion coefficient, which is specified in the dispersion package. To learn more about each of the terms in these equations, please refer to the MT3D heat transport tutorial. Here we have an existing ModFlow model. Like ModFlow, MT3DMS is structured in a modular fashion and uses a series of packages as input. Consequently, the GMS interface to MT3DMS is similar to the interface to ModFlow, and we will follow a similar sequence of steps to enter the input data. First, we will initialize the MT3DMS simulation. The MT3DMS basic transport package defines basic information such as stress periods, active and inactive regions, and starting concentration values, and is a required package. Since MT3DMS is a multi-species model, we need to define and name each of the species we will use in the model. In this case, we will use just one species named warm water. Since we are modeling heat transport instead of contaminant transport, we will use the absolute temperature of the water in place of concentration. Next, we will specify the output options in output control. We'll have the output saved at specified times. The values we input here will give us 100 output time steps. We'll now select the packages that we'll need for this model. As mentioned previously, we'll need the dispersion package and the chemical reaction package to simulate the parameters of the heat transport equation. We will also use the advection package and the source sink mixing package. We now need to specify the parameters in each of the packages. We'll start with the dispersion package. We access the dispersion package dialog by going to the MT3D menu and selecting dispersion package. Here, we will specify the dispersivity parameters of the layer. First, we set the longitudinal dispersivity array to a constant value of 0.5. The TRPT and TRVT parameters represent ratios of dispersivity in different directions. We simulate the layer being isotropic by using the same values for both. Finally, as was shown at the beginning of the video, we can use the molecular diffusion coefficient to represent thermal diffusivity. Here we use a value of 1.86 times 10 to the negative 6th. Next, we'll specify the parameters in the chemical reaction package. This is where we specify the sorption options, which we will use to represent the thermal retardation. We access the chemical reaction dialog by again going to the MT3D menu. This time we select the chemical reaction package. We'll change the sorption option to linear isothermal so we can specify the thermal coefficients. Now we need to define the data for the source sink mixing package so we can specify the temperature of the water at the injection well. This is done by selecting the cell containing the injection well, right-clicking and selecting Sources Sinks from the menu. Select MT3D point SS from the list on the left to specify that we are adding a point source. Click Add BC to define a boundary condition. As stated before, since this is a heat transport simulation, we will use the absolute temperature of the water in place of the concentration. Finally, we need to define the constant temperature at the boundaries of the model. This is done the same way that we specified the temperature at the injection well, only this time we select all the cells with the constant head boundary conditions along the top and bottom boundaries of the grid. Right-click on the selected cells and again select Sources/Sinks from the menu. We add a boundary condition just as we did before, but we'll leave the type as constant head. To specify the same temperature for all the selected cells, use the top row labeled All. Here we'll input the initial temperature of 278. We are now ready to save the simulation and run MT3DMS. We can examine the solution by viewing each time step. To better visualize the solution, we'll generate an animation showing how the warm water is pumped into the aquifer. The injected warm water is infiltrating into the aquifer. The displayed contour shows how the temperature disperses over time.